Hello and welcome to this video. In this video we're going to be covering the Edexcel A Level Maths Paper 2 from the June 2019 series. This follows on from Paper 1, which was covered in the previous video, and also assesses the pure mathematics element of the course. In question number 1 we are given these terms here, and we're asked to rearrange this in such a way where we have y equaling a function of x. Now this question here is all about index laws. This is one of the very first things that you cover in sort of A-level maths, and it really sort of builds on from what you cover at GCSE. And this question here really involves two of them. So you have a particular index law where we have a to the x multiplied by a to the y equaling a to the x plus y. Okay, this is the addition law. Alternatively, we've also got a to the x where this whole sort of term here is put to the power of y. We have this equaling a to the power of xy, where you simply times the indices together. And this is the multiplication law of indices. Now, using these laws, we're going to be sort of implementing them within this here to get it into a form where y equals a function of x, where y equals a set of terms that only involve x with all the y's on the left-hand side. Now, looking at this sort of expression here, we can clearly see that 4 is a power of 2. So we have 2 to the power of x multiplied by 4, which is 2 squared to the power of y. Instantly, you should be able to notice that this here brings in this index law here. So this here is identical to 2x multiplied by 2 to the power of 2y. And what we can see here is that this now, because we've got the same bases to these indices, a here, 2 here, and 2 here, we can simply add these indices together to the base of 2. So we have 2 to the power of x plus 2y. Okay, here, okay, so that covers the left-hand side. On the right-hand side, we have 1 over 2 root 2. And what we can see here is that we've got 1, and we've got 2 to the power of 1, aka 2, and we can see here that there's a root of 2. And like anything where you've got a root, it is simply that number to the power of a half. So we have 2 to the power of 1 times by 2 to the power of a half, and if we think about them being almost multiplied together, we have 2 to the power of 1 times by 2 to the power of a half, producing 2 to the power of 3 over 2. So we have 1 times 2 to the power of 3 over 2. And if we can think about this in such a way where we have a reciprocal of something that is to the power of something else in the denominator, we can quite easily make this 2 to the power of minus 3 over 2. Now, we have something that's incredibly simplified now. We have 2 to the power of x plus 2y, which was the left-hand side of this expression, equaling 2 to the power of minus 3 over 2. It is then clear that whatever indices we have, given the fact that the bases are the same on both sides of the equation, that x plus 2y is going to equal minus 3 over 2. And that quite simply gives us the fact that y is equal to minus a half x minus 3/4. And that there is the answer for question number 1. In question number 2, we are given that the speed of a small jet aircraft was measured every 5 seconds, starting from the time it turned onto a runway until the time when it left the ground. The results are given in this table here with the time in seconds and the speed in meters per second. In part A, we are asked to use this information to estimate the length of the runway used by the jet to take off. Now, what I think we really need to do is, before we get into this question, just look at the numbers that we're presented with. So we have time that's increasing at a constant rate of 5 seconds, okay? And we're given that speed to each corresponding time is almost changing its rate of increase. So within 0 to 5 seconds, speed is increasing by 3. Within 5 to 10 seconds, it's increasing by 5. And within 10 to 15 seconds, it's increasing by 8. And this pattern continues of this gap between speed at the start of each 5-second interval and at the end of that particular 5-second interval increasing. Okay, so almost the rate of acceleration is increasing. Now, using that pattern, using that trend, if I was to plot a velocity time graph, or in this case a speed time graph, and was to do time or speed against time, what I'd get is almost an exponential curve, okay? Shaped like this. It would be a convex curve. And it would start off at 2, 0, and it would go all the way to 25, where t equals 25, and 42, okay, this point here. Now, in terms of estimating the length of the runway used by the jet to take off, what we're ultimately asked to do is try and work out the distance, okay, the distance between t equaling 0 and t equaling 25. In any circumstance where we were given where v was a function of t, what we'd quite simply do is integrate this here within the limits of 25 and 0. And that there would give us the distance. But in this circumstance, we're not given a function, we're simply given data. And this data is organised in such a way where it quite simply and quite sort of intuitively lends itself to the Trapezium Rule, okay? And what we're really going to be using is just using this data here, substituting into the Trapezium Rule formula and come out with an estimate of the area. And that's the important thing with the Trapezium Rule. It is an estimate, okay? So with the Trapezium Rule, what we need to do is, in order to sort of measure the area under here using small trapeziums like this, is to know the height of each trapezium, also consider the width, and this is the interval of the increase of time, which in this case is 5. And what we do is divide that by 2, and we multiply it by this here, the start speed, which in this case is 2, adding that to 2 times by the addition of 5, 10, 18, and 28, all the way up until the last speed. We don't include this last speed though. So we have 5 plus 10 plus 18 plus 28. And then on top of that, we're going to add 42 onto the end. Okay? And that gives us the estimate. Okay? And if you were to calculate this out, that would come up to 415 meters as an estimate. And given that the jet accelerated smoothly in these 25 seconds, in other words, the jet accelerating in a similar fashion to the way in which I've drawn the velocity time graph, explain whether your answer to part A is an overestimate of the length of the runway used by the jet to take off. So, given the fact that this is a convex function and we're using trapeziums to calculate the area here, you can see even from this diagram that there are regions and areas where the trapezium is going above the graph itself rather than calculating what we want, which is, you know, the area under the graph. So because the graph is convex, okay, it's clear that the area of the trapeziums is going to be greater than the area underneath the graph. So that would make it an overestimate. So the answer would almost be something like overestimate. So you'd want to get, in other words, you'd want the sort of the answer to be reflective of the question straight away, and just draw dash there and just sort of explain that as the curve is convex, the area of the trapeziums is greater than the area underneath the curve. And that there is the answer to question number 2. In question number 3, we are given a sector, AOB, of a circle with centre O, radius 5, and this angle here, AOB, equaling 40 degrees. And now we're given that a student has attempted to find the area of this sector, and has sort of attempted it in this way demonstrated here. So what they've done is they've used the formula half r squared theta, which if you've studied radians you should be aware of, and have basically substituted the radius as 5, which is correct, and the angle theta here for 40 degrees. And they've come up with an answer of 500 centimeters squared. And for part A, what we're asked to do is find or explain the error made by the student. Quite simply, this formula here, half r squared theta, is the correct formula for the area of a sector. The use of 5 as r in this case is absolutely correct, but the fault lies in their use of 40 degrees for theta. This formula here, half r squared theta, is only valid when the angle that is being considered at the center of the sector is measured in radians. Okay, and here, quite simply, the angle that is given is measured in degrees. So what the answer would be for this is that the formula is only valid when angle AOB is given in radians. Yeah. So if this was given in radians, it would suffice. For part B, work out a correct solution. Now there are two ways in which we can do this. We can either convert this into radians by multiplying 40 by pi over 180, or equally what we can do is just simply, like you would be expected to do in GCSE, do 40 over 360, because a total circle would have 360 degrees within it. So this as a proportion would be 40 over 360, and just use that age-old formula of pi r squared. So we times that by pi, times that by 5 squared, and that there would give an exact solution of 25 pi over 9 centimeters squared, because the unit of the radius we used in this case was centimeters. And that there is the answer for question number 3. For question number 4, we're given two curves. We're given the curve C with parametric equations x equals 10 cos t and y equals 4 root 2 sine t. And we're given the circle C2 with equation x squared plus y squared equals 66. In other words, a circle with center 0, 0 and radius root 66. And we're told that these two curves intersect at 4 distinct points as shown in this diagram here. And we can see that those are here, 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 and this point in the fourth quadrant here marked S. And for this question, we're ultimately asked to find the coordinates of this point S. And the way in which we're going to be doing this is we're going to be solving it in a very similar way to the way in which we'd solve a simultaneous equation question. So we'd get this x equation here, we'd get this y equation here, and simply just substitute it into here, sort of rearrange things to find a value of t that satisfies both of these equations, plug it into here, get a value of x, get a value of y that satisfies this point S here, which has a positive x value and a negative y value. So without much further ado, let's do it. So we have 10 cos t squared plus 4 root 2 sine t squared, and that's going to equal 66. And to square this, we'd have to square 10, so that would make 100 cos squared t plus 4 root 2 squared, that would make 32 sine squared t. So we'd square this, square that, square this, square that, and just multiply the relevant ones together, and that's going to equal 66. And now what we're going to be doing is we're going to be using our most fundamental trigonometric identities, ones that at this stage you should be knowing like the back of your hand. So we have 100 cos squared t, and we're going to add that to 32, 1 minus cos squared t, which as you should know is equal to sine squared t, and that's going to equal 66. We're going to rearrange this, so we're going to expand this out and then rearrange. So we have 100 cos squared t plus 32 minus 32 cos squared t, and that's going to make 68 cos squared t equaling 34. So 66 minus 32. And now what we're going to be doing is we're going to be taking that one step further by 34 divided by 68, so dividing both sides by 68. And that makes cos squared t equaling 32 over 68, which is equal to a half. And then we're just going to square root both sides. So cos t is going to equal plus or minus, remember the plus or minus here, 1 over the square root of 2. And now, because we've got this sort of expression here, or this equation here, we're going to be just sort of plugging into the calculator really. So we're going to have the arc cos of 1 over root 2. Okay, we're going to try the positive value first, and that gives us a value of t of pi over 4. okay? And when we substitute it into these parametric equations here, we should be getting a positive value of x and a negative value of y, as I've mentioned, because the point of intersection that we're interested in is in the fourth quadrant. So x is going to equal 10 cos pi over 4, which is going to equal 10 times by 1 over root 2, which is going to equal 5 root 2. And that's correct because that is a positive value. And we're going to be putting in y as, and I'm just going back to the parametric equation here, 4 root 2 sine pi over 4. And that's going to equal 4, okay? So it's clear that the y value we've got here does not necessarily produce a negative or a negative number. So ultimately what we've got here, the intersection that we found is this one here, okay, where we've got 5 root 2 as the correct x value, but instead we've chosen the positive y value as opposed to the negative y value. Quite simply, the y value is going to be the reflection of this in the x-axis. So if we just simply negate what we've got here as minus 4, that should give us the correct value of y. So we got the positive y value, but we're interested in the negative version of that, which is going to be the fourth quadrant and is therefore going to be the negative of whatever we found there, which was 4, which became minus 4. So the coordinates of S are going to be 5 root 2 minus 4. For question number 5, we're given what seems like quite a nasty question. We're given this curve here, y equals the square root of x, and we're told that the point P, xy, lies on this curve. And we're told the rectangle shown on figure 3, this shaded rectangle here, has height y and width dx, okay? In other words, this here is not so much dx as it is delta x. And what we're asked to do is calculate, as dx tends to 0, what the sum of these squares are between 4 and 9. Now, again, like I've mentioned, this seems like quite a nasty question. But what this really requires, and what the hardest part of this question really is to understand what this means. And what this fundamentally means is something that's quite simple. Width of delta x, okay, and this is the Greek letter here, delta, ultimately means a width that is, as it tends to 0, becomes infinitely small. So what we get are almost infinitely small sort of rectangle widths here, between 4 and 9, that each have, again, a width that is infinitely small, but a height that is equal to the square root of x at that particular moment in time. So, in other words, what we get are rectangles that are very, very, very narrow, all the way between 4 and 9, and we add them together, okay? And that's what this sigma represents, the addition of these rectangles together, okay? The area of them together. And what that does is that it gives us the exact area of underneath this curve between the points of 4 and 9. Now, if you haven't pointed out already, that is essentially the integral of the square root of x, which we put as x to the half, between the limits of 9 and 4. Okay, and that's ultimately the hardest part of this question, is to look at this and realise that it is fundamentally the integral of x to the half between the limits of 9 and 4. And now what we can do is just sort of take this further by solving this very, very simple integral. Compared to the other ones that we have to deal with, it's very simple. So we add 1 to the half, which makes 3 over 2, and then we divide this whole thing by 3 over 2 to make 2/3 multiplied by x to the power of 3 over 2. And we're going to be substituting our limits of 9 and 4 in there, and that makes 2/3 multiplied by 9 to the power of 3 over 2 minus 2/3 multiplied by 4 to the power of 3 over 2, and that's going to equal 38 over 3. And that there is the answer to what seems like initially a very complicated question. For question number 6, we're given this function here, g of x, which is formed of two parts. It's formed of the parabola x minus 2 squared plus 1 for values of x which are less than or equal to 2, and is formed of the line 4x minus 7 for values of x which are greater than 2. For part A, we are asked to find the value of g of 0, and this is a composite function. And because this is a composite function, first what we need to do is find the value of g of 0, and then substitute what number we get there into g to find the overall value of this here. G of 0 is going to equal, well, first we need to consider the fact that 0 is less than or equal to 2, so we'd need to substitute 0 into this part of the curve in order to get this point here. 0 minus 2 is minus 2. Minus 2 squared is equal to 4. 4 plus 1 is going to equal to 5. So g of 0 is going to equal 5. G of 0, okay, is going to equal g of 5, okay, and because 5 is greater than 2, you'd want to put it into this part of the function. So 4 times 5 is equal to 20. 20 minus 7 is going to equal to 13. And that there is the value of g of 0. For part B, what we're asked to do is find all values of x for which g of x is greater than 28. So if we draw a line of y equals 28, so if we just draw a horizontal line there, where that there is 28, it's clear that the function is greater than 28 at 2 points. It's greater than 28 here, and it's greater than 28 here. So if we were to find the points of intersection, here and here, all sort of values of x which are less than this value here would make the function g of x greater than 28. And all values of x which are more than the value of x here would again make the function more than 28. And since there are 2 points of intersection for the x minus 2 squared plus 1 of the function, and the 4x minus 7 part of the function, it's clear that we do need to apply the inequality to both parts of the function. So for the first part, we have x minus 2 squared plus 1 being greater than 28. We rearrange this, subtract 1 from both sides, to have x minus 2 squared is more than 27. Square root both sides, x minus 2 is greater than plus or minus 3 root 3. And remember here, we're looking for the negative value of x, right? Here, this point of intersection, x is negative. So we're going to be taking the negative square root, okay, so minus 3 root 3, and we're going to be adding 2 onto that. So x is going to be greater than 2 minus 3 root 3, okay? And for the second sort of range, what we're going to be doing is we're going to be using this part here, 4x minus 7, the linear part of the function. And that's going to be greater than 28. 4x is therefore going to be greater than 35. X is therefore going to be greater than 35 over 4. And that there forms the two parts of our answer for B. For C, we're asked to explain why h has an inverse but g does not, h being this function here. And if we look at h, we can see that x minus 2 squared plus 1 and the domain that we've been restricted to, which is x is less than or equal to 2, is identical to the first part of g of x. In other words, this sort of curve here up until this point. And we're asked to explain why h has an inverse, why this would have an inverse, but g of x does not. In other words, why the whole thing wouldn't have an inverse, but this part of the function would. And to solve this question, or to answer this question, we really need to start defining parts of the function with one-to-one, one-to-many, many-to-one characteristics. H, being this part here, is a one-to-one function. Each input has a distinct output. The whole function, however, okay, becomes a one or it becomes a many-to-one function. So many values of x correspond to one value of y. We can see that here with y equaling 28. We have a value of x here and we have a value of x here, which both correspond to a y value of 28. So the whole function is a many-to-one, but h alone is a one-to-one. That means that if we were to reverse what the characteristics suggest, h, or the inverse of h, would remain a one-to-one function, but the whole of g of x would become a one-to-many function. And if we can remember our facts correctly, a one-to-one or a one-to-many function isn't a function at all, but is a mapping. Okay, so it remains as a mapping. So our answer is basically going to involve that h minus 1 exists. So the inverse of h exists because h is a one-to-one function. Okay, and stressing the fact that it is a function. G minus 1 will not exist. Okay, because g of minus 1 is a many to one function. So that means that the inverse of g will be a one-to-many function, which isn't a function, but is instead a mapping. For part D of this question, which is the final part of this question, we're asked to solve the equation h, or the inverse of h is equal to minus a half. The inverse of h is x minus 2 squared plus 1. And to find the inverse of this, we need to use our old trick of setting y equal to the function and then rearranging this to make x the subject of the formula. So if we subtract 1 from both sides, y minus 1 is equal to x minus 2 squared. And if we were to square root both sides, we'd get that x minus 2 is equal to plus or minus the square root of y minus 1. And therefore x is equal to 2 plus or minus the square root of y minus 1. And this is going to be equal to a half, okay? But one thing we need to do is we need to remember the fact that we've set that y is equal to this. So the inverse is going to be 2 plus or minus the square root of x minus 1, okay? Because we've used the old trick of saying y equal to this function. We've rearranged it to make x the subject of the formula, but at the end we need to remember to substitute x instead of y. And that there is going to equal h minus 1x. And that there we've been told is equal to not a half, but a minus of a half. Okay, and we're just going to be simply rearranging this around. We subtract 2 from both sides, we square this value here, and we add 1, and that gives us an x value of 7.25. And that there is the answer for question number 6. In question number 7, we're told that a small factory makes bars of soap. On any day, the total cost to the factory, y pounds, of making x bars of soap is modelled to be the sum of 2 separate elements. These are the fixed cost, which we'll name A, and we have added to this the proportional cost, which is proportional to the number of bars of soap that are made that day. In other words, this is the marginal cost of production. You know, each additional unit of bar brings an additional cost, and this K represents that cost. So for part A, what we're asked to do is to write down a general equation linking y with x. So I guess the most sensible way to approach this would be to have y on one end of the equation. This would be the cost of production, the total cost to the factory of producing these bars of soap. And we're going to add the fixed cost to that, A, to the proportional cost. And the proportional cost is going to be this K value, this cost of producing 1 bar, multiplied by x, the number of bars we're producing. So we get kx. And this y equals a plus kx tells us the fixed cost and the additional costs that are brought about depending on how many bars of soap this factory produces. For part B, what we're asked to do is to show that y is equal to 0.84x plus 428. In other words, to show that k is equal to 0.84 and that a is equal to 428. To help us with this question, we're given some information. We're told that the bars of soap are sold for £2 each. We're told that on a day when 800 bars of soap are made and sold, the factory makes a profit of £500, and that on a day when 300 bars of soap are made and sold, the factory makes a loss of £80. So we just need to use this information to again demonstrate the fact that K is 0.84 and that A is equal to 428. Now, because here in this information we're associated with profits and loss, we really need to calculate the difference really between the total revenue we're bringing and the costs that are represented in this equation here. So on line 1, where we're told that when 800 bars of soap are made and sold, the factory makes a profit of £500. It's the difference between 800 multiplied by 200, which gives us the total revenue that the factory has brought in, and the costs that are brought around as a product of producing these 800 bars of soap that give this £500. And it's a similar sort of line of thought for the second part of this information here. So applying that logic, we're told that 500 is equal to 800 times by 2, which gives us the total revenue that the factory has brought in, which is 1,600. Now we're going to subtract that from the costs, okay? We're told that X is obviously 800 because we're producing 800 bars of soap. So from 1,600, I'm going to remove the costs, and that's going to be A plus 800K. And we're going to be doing something similar to this one here. We're told that we have a loss, so that's going to be negative of 80 is equal to 300 times 2. So that means the factory is bringing or making a total of £600. But from that 600, we're going to deduct our costs. So that's going to be A plus 300 this time, 300K. And these form our two equations. Now what I'm going to be doing is I'm just going to be sort of moving these around, rearranging it so we get our unknowns on the left-hand side and some sort of number on the right-hand side, so we can solve it or solve them as simultaneous equations. So equation number 1 becomes A plus 800K is equal to 1100, and equation number 2 becomes A plus and in this case it's going to be 300K is equal to 680. And this is a very simple simultaneous equation here. We just take away 2 from 1. This cancels that. Get 500K is equal, becomes equal to 420. And then quite simply we can just work out that K is 420 over 500, which if you put that into your calculator equals 0.84. Okay, so we've proven the first part of it. And now what we're going to be doing is just going to be putting that back into the one of the equations. We'll just put it into equation number 1. So that A plus 800, put that in brackets, multiplied by this value of K that we've just found out, is equal to 1,100. 1,100 minus 800 times 0.84 gives us a value of A as 428, if you put that into your calculator. And that hence proves that y is equal to 0.84x plus 428. For part C, what we're asked to do is, with reference to the model, interpret the significance of the value 0.84 in the equation. 0.84, we likened that to the K that we had sort of initially put forth in part A. And when it came to K, we associated it with a proportional cost to the number of bars of soap that are made that day. Okay? And in simple terms, all this really means, like I've already mentioned, is this idea that 0.84 represents the additional cost of producing one extra bar of soap. And just to be on the safe side, it's worth sort of just putting the units there in pounds. Yeah. If you do economics or business, this is usually termed the marginal cost of production. For part D, we're asked to find the least number of bars of soap that must be made on any given day for the factory to make a profit that day. Okay, and for this to for a profit to be made, we need a certain number of bars of soap, we'll call it N, multiplied by 2, and once we take away the cost from that, the difference must be more than 0. Okay, in other words, the total amount of money you're bringing in must be greater than the amount that's being taken out through costs. So we have 2, which is the price of 1 bar of soap, multiplied by the number of bars of soap we're selling, n, the number that we're trying to find out, and that gives us our total revenue. Okay, and from that we're going to be taking away the costs. We saw that in this case A is 428 and K is 0.84, and we're going to be timesing 0.84 by the n value we have here. And the difference between the revenue and the costs must be greater than 0 for a profit to be made. I'm just going to be taking 0.84 away from 2n. That gives us 1.16n, and going to be taking away 428 from that, and that has to be more than 0. And we're just going to be rearranging this as if this was an equal sign. And we get that, and that gives us an n value of 428 over 1.16, which equates to 369 bars of soap. Okay, and that's the answer to that question. Question number 8 is quite a tricky one. It's all about summations. In part I, what we're asked to do is find the sum to infinity from r equals 4 to infinity of 20 multiplied by a half to the power of an r. Now, if you don't know how summations work, what you do is you take the bottom number, in this case which is 4, you put it into the expression, then you take the next number, which is 5, you put that into the expression, and you keep on going all the way up until whatever number's at the top of this capital sigma, and you add each of those results together. For part I, what we're given is a summation where we've got a number that isn't 1 at the bottom. We're given a number that has 4, or we're given a summation that has 4 at the bottom, and we're asked to find the sum to infinity between 4 and infinity. Whenever you're given this sort of question in an exam, what is almost always the case is for you to have to convert this into a summation where you've got 1 at the bottom. So if we've got infinity and r equals 4 as the summation, we can break this down into a summation that goes from 1 to infinity, and from that we're going to subtract a summation that goes from 1 to 3. But before we get into applying this summation or these summations to this expression here, what we really need to understand is that this here represents a geometric sequence. And I think the best way to illustrate this is to just work a few of these terms out. So if we were to substitute 1 into this to work out the first term of our sequence, we'd get 20 times half to the power of 1, which would be 10. The second term, substituting 2 into this, would give us 5. The third term, substituting 3 into this, would give us 2.5, and the terms would continue on, each being a half of the previous term. So if we want to apply any sort of geometric sequence formulas into here, it'd be worth us noting that the first term, denoted A in all formulas, is 10, and the common ratio is going to equal a half. Now, because we've got infinity here, what we're looking at here is the sum to infinity. And because r in this case is between 0 and 1, what we are looking to do is really use the sum to infinity formula, which is a over 1 minus r, and that would give us the value of this here. And that would be equal to 10 over 1 minus a half, which gives us 20. Now, to calculate this out, because obviously the difference between 1 and 3 is not that large, what we can ultimately do is just substitute 1 into the formula, add that to whatever we'd get if we substituted 2 into this formula, and add that to whatever we'd get if we substituted 3 into this formula. And quite handily, we've already written those sort of 3 terms of the geometric sequence out. So from 20, what we'd want to do is we'd want to subtract 10 plus 5 plus 2.5. And that would give us an answer of 2.5 if we were to put that in the calculator. For part II, what we're asked to do is to show that the summation from n equals 1 to 48 of this quite messy looking logarithmic expression here is equal to 2. Now this is quite different to the previous summation where we didn't have 1 at the bottom and we had infinity at the top. Here we have 1 at the bottom and 48 at the top, which means that we don't have to split this up into 2 separate summations, and we don't have to involve all sorts of sums to infinity formulas like we did on the previous part of the question. So really with this, what we're going to be doing is we're going to be substituting 1 into here. We're going to be adding that to what we get when we substitute 2 into here, all the way up until 48. Now, oftentimes, you would never be expected to do that sort of manually. You would be expected, like we did in the previous sort of example, find a pattern, in this case using the sums to infinity, splitting the sort of summation off into parts. But in this case, it seems quite difficult to find that sort of pattern. And whenever you find a difficulty in finding, a pattern within quite a difficult and tricky looking summation, what the first and most obvious step would be is to sort of just start plugging numbers into here. Plug 1 into here, plug 2 into here, add the terms together, skip a couple terms, see what happens when you plug 47 and 48 into here, and just sort of start messing around with things until you start to notice something. So let's do that. So say if we plugged 1 into this, what would we get? So we'd get log base 5, plugging 1 into there would get 3 over 2. We'd add that to what we'd get if we plugged 2 into there, which would be log base 5, 4 over 3. And let's skip a couple terms now, and let's find ourselves at 47. So we'd get log base 5, would get 49 over 48. And say if we were to put a final number in there, which is 48, we get log base 5, 50 over 49. So what we can see here is that there are sort of patterns taking place, and these patterns are sort of noticeable at this point. But I think the most obvious way to notice the patterns within this mess here is to sort of break these logs down into their into finer components. And to do that, we obviously need to use log laws. We can see that we've got log base 5 of, a number divided by a certain number, so we need to use our subtraction law in that place. So log with base 5, 3, multiply, and from that we're going to be subtracting, log with base 5, 2, and then we're going to be adding log with base 5, 4, and then from that we're going to be subtracting log with base 5, 3, and then I'm just going to be carrying on with the sort of the final 2. So we'd add log base 5, 49, subtract log base 5, 48, add log base 5, 50. I know this seems slightly tedious, but I assure you that we'll get there. And we're going to be subtracting log base 5, 49. Now what we can see is that this term here and this term here cancels out. This term here and some term here will cancel out. And just applying the same logic really, this term here and this term here will cancel out. Some term over there will cancel out with some term over there. And what we're left with is log with base 5, 50. And from that we're going to be taking away log with base 5, 2. Okay, and it's quite a tedious process. I understand this is quite complicated, so feel free to pause the video, rewind and re-watch it how I came to form this. But from here, what we're able to do is to almost reverse what we did and use our subtraction law again to find log base 5 of 50 over 2. And from that, we get that log base 5 is equal to 25. And from this, we can actually sort of work out an answer. 5 to the power of something is 25, and that something is obviously going to be 2. Okay, equally, you can just put it into your calculator. So there we go. We found that this summation does indeed equal 2, and that's the answer for that question. For question number 9, we're told that a research engineer is testing the effectiveness of the braking system of a car when it is driven in wet conditions. The engineer measures and records the braking distance, d meters, when the brakes are applied from a speed of v kilometers per hour. the graphs of d against v and the graphs of log base 10d against log base 10v are plotted, and we can see them here. Explain how figure 6 would lead the engineer to believe that the braking distance should be modelled by the formula d equals k multiplied by v to the n, where k is approximately 0.017. So, in essence, in part A, what we're asked to do is look at what we've been given here in figure 6 and try and relate this formula to this here. So what we can see is that where we've got y as log 10d and x as log 10v, between x and y there is a linear relationship. So if we were to apply logs to this formula, manipulate it in such a way where we were able to demonstrate this linear relationship, we would be able to validate the engineer's belief. So what I'm going to be doing is I'm just going to be applying logs to both sides of this, this formula. So we'll have log base 10d equals log base 10k multiplied by v to the n. I'm using logs of base 10 here simply because the graph itself uses logs of base to the 10. Here we can see that we have a term that's being multiplied within this logarithm. So we're just going to be applying our addition rule here. So we have log base 10 v to the n plus log base 10 k. And we're going to be taking this index now to the start of this log here, using our index law that we'd associate with logarithms. And quite simply, we've already demonstrated a linear relationship. So in this case, as was mentioned, log 10d becomes our y and log 10v becomes our x. So if we have log 10d as our y, that's going to equal to some constant that's multiplied by our x. It's clear that this constant here becomes our gradient. And then this log 10k, which is a constant again, will become our y-intercept. So if we associate log 10d with y, n as our gradient, and log 10v as x, log 10k will become our y-intercept. And in that relationship, we've demonstrated some sort of linearity. And taking that one step further now, we know that log 10k is our y-intercept. We know that the y-intercept is minus 1.77. So we know that log 10k is equal to minus 1.77. We know then that 10 to the power of minus 1.77 is going to equal k. And k is therefore 0.01698, which to two significant figures produces 0.17, validating the engineer's claim. So next, for part B, what we're asked to do is to use data given on figure 5, namely this point that's been marked out here, to find a complete equation for the model, giving the value of n to three significant figures. In other words, we're just going to be rewriting this, but with 0.017 as k, and some value that we found out as n in that case. So we know that d is going to equal 0.017 multiplied by v to the n, and quite simply we're just going to be substituting these points in, 30 and 20. So we know that a distance of 20 is equal to 0.017 multiplied by 30 to the power of n. We're going to apply logs to both sides. So we have log 20 is equal to log 0.017 multiplied by 30n, and just using the exact same sort of principle of, you know, the multiplication rule, and then you've got the index law to find that n log 30 is going to equal log 20 over 0.017. And then we divide both sides by log 30 to give a value of n as 2.08 to three significant figures. And then just writing that out in its full form, we know that d is going to be equal to 0.017 multiplied by v to the power of 2.08. And that should be the answer to part B. For part C of this question, we're given an extra sentence to read. We're told that Sean is driving this car at 60 kilometers per hour in wet conditions when he notices a large puddle in the road 100 meters ahead. It takes him 0.8 seconds to react before applying the brakes. And we're told in part C to use our formula, d equals k multiplied by v to the n, to find out if Sean will be able to stop before reaching the puddle. So from the point he sees the puddle to the point the car stops, we ultimately want that distance to be less than 100 meters, so it stops before he approaches the puddle. I guess the first step to this would be turning this 60 kilometers per hour into meters per second. We're dealing with meters here, we're dealing with seconds, we want everything to have the same sort of unit. So for part C, we have 60 kilometers per hour. And in order to turn this into meters, first of all, we have to times it by 1,000. And then in order to turn it into, in order to turn this hour into seconds, we need to ultimately realize that there are 3,600 seconds in an hour, and divide this by 3,600. And this here gives us our meters per second. Okay, this is how fast Sean is traveling in the car in meters per second. And what we need to do now is find out the distance it takes for him to, or the distance it takes between him noticing the puddle and actually reacting to it and pressing the brakes. And that will be the speed that we've calculated multiplied by the time. So we have this here multiplied by 0.8 seconds, and that will give us our distance of 13.33 meters. This is the distance that Sean travels from him noticing the puddle to actually applying the brakes and reacting to what he's noticing. The next part of this question is to know how long it takes between him pressing the brake and actually coming to a stop once he's traveling at 60 kilometers per hour. And for this, what we really need to know is, or what we really need to use, is this formula that we've come up here, where d is equal to 0.017 multiplied by, in this case, v, which will be 60 because we're told that v is kilometers per hour, to the power of 2.08. And that there, if you put it into your calculator, should come up with a value of 84.92 meters. So if we add this and add this together, this is the total distance between him noticing the puddle and the car actually coming to a close. And if we added these together, we'd come up with a value of 98.25 meters. And now this falls just short of the 100 meters that was his distance when he noticed it, or when he noticed the puddle initially. So it is clear that Sean will stop before reaching the puddle. And that there is the answer for that question. Question number 10 shows a sketch of triangle OAB. And we know that the point C is such that OC is equal to 2OA. And the point M is the midpoint of AB. So we have the point M there. And the straight line through C and M cuts OB at the point N. So what we really need to do before anything is just start manipulating or start illustrating this diagram, because we're given quite a very sort of simple and basic figure of the vector itself. So we're told that OC is equal to 2OA. So I guess what happens is the line OC is going to start from O and is going to be 2 of OA. So it's probably going to just double the side there. And the triangle itself will probably end up closing off like that then. So we have OA, and here we will have C, which we'll mark in now. And that will close in at B, and then we have M as the midpoint of AB. And we're told that the straight line through C and M cuts OB at the point N. So we need another line going through C and M, and that's going to cut M. So we have the point N here. And what we're asked to do in part A is to find CM in terms of A and B. And before we really sort of get on to exploring that, let's mark in A and B. So we know that, and we'll do this in red just for purposes of clarity, we know that OA is going to equal to A, and we know that AC is therefore also going to equal to A because we know that OC is equal to 2 of OA. And that OB, this huge distance here, is going to equal B. Okay, so we're asked to find CM in terms of A and B, CM being this line here. CM, okay, as a vector, is equal to CA, so going from there to there, and then on top of that AM. Okay, so CA plus AM. And so AM, okay, itself is half of AB. So we can further break that down by saying CM is equal to CA plus half AB. We already know that CA is going to equal minus A. Okay, if A is pointing in this direction, if we were to go backwards, that would produce minus A. And we're going to add to that half of AB. AB being this here. AB itself is minus A plus B. And if we were to expand this out and add minus A to minus a half A, and then on top of that adding half B, we'd get a overall answer of minus 3 over 2A plus half B. For part B, we're asked to show that ON, which is the vector from here to here, is equal to 2 minus 3 over 2 lambda A plus half lambda B, where lambda is a scalar constant. So I guess what we really need to do is apply similar logic to ON. And ON is equal to, and if we break this down, it's going to be equal to OC plus CN, okay? And I guess what we really need to do now is apply this constant, this scalar constant to this vector. So if we know that ON is equal to OC plus CN, we can apply this scalar constant in such a way where we can say that ON is equal to OC, a vector that we know as 2A, plus lambda CM. We know what CM is, we've just calculated it. And because CN is a particular multiple of, in terms of its magnitude, a particular multiple of CM itself, we can apply that scalar constant to CM. So we know that ON is equal to OC plus CN, and then from that we took that it's equal to OC plus lambda CM. And really from that we can just start using the values that we've either been given or have found out. So OC is equal to 2A. Okay, and in actual practice you'll be doing lines underneath each of these. So we'd have 2A, and then CM itself is something that we've already calculated as lambda. Okay, and we're applying that scalar constant to it because it's slightly longer than CM itself. And if we were to expand this out, simplify it, we know that 2 minus 3 over 2 lambda A plus half lambda, because we've multiplied this out and simplified it, or collected like terms, should I say, B is going to equal ON, okay, this vector here, and that completely satisfies this here. Hence prove that ON and the ratio between ON and NB, the ratio between this and this, is 2 to 1. So the length of this is twice the length of this. In other words, this covers 2/3 of the length, and this covers 1/3 of the whole length of OB. We know that in this case, OB itself, okay, OB itself the value of the A component in that case is 0. Okay, and we know that because for OB, the vector that we're considering in this case is B only. A is a completely different vector that we aren't considering for this particular vector here. So we know that 2 minus 3 over 2 lambda is going to equal 0. And from that we can see that 2 is going to equal 3 over 2 lambda. And that makes lambda as 4/3. We know that OB is going to equal B. We know that ON in that case, with lambda equaling 1/3, is going to be 0 multiplied by A. Okay, and that's going to be added to 2/3 B. And that gives a value of 2/3 B, and that's equal to ON. And on top of that, we know that OB, the whole distance is B. So if this is 2/3 B, and this whole distance is B, that means that this is 1/3 B. And the ratio between this and this, between 2/3 and 1/3, and once we multiply both sides of this ratio by 3, is 2 to 1. And that verifies this, this statement here. In question 11, we're given figure 8, which shows a sketch of the curve C with equation y equals x to the power of x restricted to the domain where x is more than 0. In part A, what we're asked to do is find, by firstly taking logarithms, the x-coordinate of the turning point of C. In other words, the x-coordinate of the point that looks as if it's about there. So this is slightly different to the way in which we'd normally approach this sort of a question, where we'd simply just take the derivative, set that equal to 0, rearrange it a little bit until we get an x-coordinate. In this particular circumstance, they want us to take logarithms first. And I guess the most simple way of doing this really is just to take luns of both sides, because we know that luns do tend to differentiate really, really nicely. So if we get y equals x to the power of x and just put luns on both sides of that equation, we know that ln y is equal to ln x to the power of x. And just using our standard index law for, the one that would associate with logarithms, we'd know that x ln x would be equivalent to ln x to the power of x. And really now what we need to do is now apply our sort of differentiation, and the way in which we do so, where we've got a function of y and a function of x happening on both sides of an equation, is through implicit differentiation. So ln y would differentiate to 1 over y. And remember, we'd almost differentiate this y as if it was an x, and then just add dy over dx next to it. That is the process of implicit differentiation. Here we'd need to use product rule, so we'd have x multiplied by the derivative of ln of x, which is 1 over x, so we'd have x multiplied by 1 over x, which gives x over x, which is 1. And we're going to add that to ln of x multiplied by the derivative of this here, which is 1. And that gives us 1 over y dy over dx is equal to ln x plus 1. And because we're interested in the x-coordinate of the turning point of C, what we're going to be doing is that we are going to set this equal to 0, okay? Because dy over dx, when you're at the turning point, is equal to 0. So we multiply 0 by 1 over y to make 0. So what we get is that ln x plus 1 is equal to 0. And then what we can do there is that ln x equals minus 1. So x is going to equal to e to the power of minus 1. Okay, not forgetting that ln is quite fundamentally a log of base e. And that there is the x-coordinate. For part B, what we're asked to do is, so we're given the point alpha 2 lies on C, and we're asked to show that 1.5 and 1.6 is the range of alpha. So what we need to do here is, this is slightly different to the standard way in which you'd be expected to answer this sort of question, where you'd have a root. Here we have just a sort of general standard point on the curve. So we're going to be substituting 1.5 into here and 1.6 into here. And if both answers give an answer that's on either side of 2, given the fact that the curve is continuous, we know that alpha lies between those points. So if we had 1.5 to the power of 1.5, remembering that our function is y equals x to the power of x, the y value is going to equal 1.837, which is less than 2. And for our second, or for our upper limit of the range, which is 1.6, we'll have 1.6 to the power of 1.6, and that's going to equal 2.121, which is greater than 2. So, you know, the curve contains the points (1.5) and 1.8 and 1.6 and 2.1, and at P y equals 2, since the curve C is continuous, we can therefore confirm that alpha is indeed between 1.5 and 1.6. For part C, we're given that there is a possible iteration formula that can be used to find alpha. And this formula starts with x as 1.5. So what you do in this iteration formula is do 2 times 1.5 to the power of 1 minus 1.5, and then just put your answer back in as xn, and repeat that until you end up with some sort of constant or with some sort of unchanging number, alpha, provided that the iteration is, of course, successful. So we're asked to start with x1 equaling 1.5 and go all the way to x4. This is one that is quite easily done on the calculator. X1 is equal to 1.5. So just using that formula above, x2 is going to equal 2 times by 1.5 to the power of 1 minus 1.5, which is going to equal minus 0.5. And that gives us an answer of 1.633. And now, because we've already gone through the process of one iteration, the exam board at Edexcel, they do permit you to be able to just put the rest into your calculator. So if we were to put this back into our calculator, applying it within that iteration formula seen above, we get an x3 value of 1.466, and we get an x4 value of 1.673. Okay, and that there is our answer for that part of the question. So we can ultimately see that it's sort of bouncing between numbers that are in the range of 1.5 and numbers that are in the range of, say, 1.6 or 1.7. Part D asks us to describe the long-term behavior of x of n. So it literally is using that logic precisely. We can see that each iteration is essentially bouncing between different sort of values that are within common ranges. So 1.5 and 1.466 are in a similar range, and 1.63 and 1.673 are in a similar range. So we can see that xn oscillates. That is one possibility that the exam board would permit. Equally, periodic is another, and non-convergent is another one as well. So you can have either of these. I believe it's a 1 marker. No, it's a 2 marker. But yeah, this should be able to sort of give you one of the marks, and then you can just sort of build on it further by saying that this occurs between the values of 1 and 2. Okay, and that there is the answer for question 11. For question number 12, we're given a really nice trig identities question. So we're given that cos 3 theta over sine theta plus sine 3 theta over cos theta is identical to 2 cot 2 theta. And for part A, we're asked to prove this relationship. So the way in which I'd approach this question is fundamentally to just add these fractions as you would any normal fraction. So we'd bring them as one fraction, so we'd do cos 3 theta times by cos theta, added to sine 3 theta times by sine theta, over the denominators multiplied with each other. And now it's all about trying to figure out patterns. Here, okay, the more perceptive amongst you would find that there is a very vague use of a compound sort of subtraction formula for cosine. And that's that cosine 3 theta minus theta is equal to this. And really what we know now is that the bottom as well also does involve some sort of compound angle formula, specifically a double angle formula, where sine theta cos theta is the same as a half sine 2 theta. So we can simplify this down into cos 2 theta over a half sine 2 theta would then be equal to 1 over a half tan theta, which would of course then equal to 2 cot, just remember that 2 there, 2 cot 2 theta. For part B, we're asked to use our result here to solve for between the angles of 90 degrees and 180 degrees the equation cos 3 theta over sine theta plus sine 3 theta over cos theta equals 4. So just equating both sides of this, we know that this here is equal to 2 cot 2 theta. We've proven that is equal to 4. And obviously when you're solving these sorts of equations, it isn't useful to have your sort of reciprocal trigonometric functions. So just sort of make it the normal ones. That is the sort of common practice with those sorts of questions. And therefore we know that tan 2 theta is equal to a half, and we get a value of 2 theta then as 26.6 degrees. But the range in which, or the range of theta that we're looking for is between 90 and 180 degrees. So what we'd do is we'd just quite simply just add on 180 degrees to this, because we know that tan repeats every 180 degrees. So 2 theta is going to equal this 26.6 degrees, and also 206.6 degrees, just adding on 180 to that. Therefore, we get a value of theta as 13.3 degrees and 103.3 degrees. And that's given there. And that there is the answer to question number 12. In question number 13, we are told that a manufacturer produces a storage tank. The tank is modelled in the shape of a hollow cylinder closed at one end with a hemispherical shell at the other end, as shown in this figure here. The walls of the tank are assumed to have negligible thickness. The cylinder has a radius of r meters and a height of h meters, and the hemisphere has radius r meters. The volume of the tank is 6 meters cubed. In part A, what we're asked to do is that we're going to use this information provided here to show that the surface area of the tank in meters cubed is given by this formula here, 12 over the radius plus 5/3 pi r squared. I guess really what we need to do here is that we need to take the information we're given and start to come up with some sort of equation. We're told that the volume of the tank is 6 meters cubed. So what we can do is we can say that 6 is going to be equal to pi r squared, okay, which is going to be the area here, multiplied by h. That will give us the volume of this cylinder here. So we have pi r squared h, and we're going to add that to the volume of this hemisphere here. And this hemisphere is going to be half the volume of the sphere, which is going to be half of 4/3 pi r cubed, and that's going to be a grand total of 2/3 pi r cubed. And we're going to add that to pi r squared h in order to give us 6. And what we need to do now is come up with a sort of similar formula, or using the information that we at least do have access to for A. And for this, what we really need to realise is the area is going to be formed of 3 main things. It's going to be formed of pi r squared, this circle at the bottom. It's going to be formed of the surface area of this hemisphere here, which is going to be half of 4 pi r squared, which is going to be 2 pi r squared. So we can add them together to make 3 pi r squared. But the most tricky part really is going to be the 2 pi r h that is going to be this sort of curved part here. Okay, the main face of the cylinder. So it's going to be 2 pi r h. And I guess now what we can do is that because we know that the formula for the surface area here does not have an h term, we can use this first equation in order to rearrange things in such a way where we can substitute a value for h in. So we know that the area is going to be 3 pi r squared plus 2 pi r multiplied by 6 minus 2/3 pi r cubed over pi r squared. This here and that there will cancel out. So we know that the area is therefore going to be 3 pi r squared plus 2 pi multiplied by 6 minus 2/3 pi r cubed over pi r. And now what I'm going to be doing is I'm going to be sort of expanding this out and sort of simplifying things. And that gives us a value of a for 3 pi r squared, and just sort of expanding this out, simplifying things to form 12 over r minus 4 pi r squared over 3. And sort of collecting these terms here, what we can find out is that this area is going to equal 12 over r plus 5 pi r squared over 3. And if we take what we found there and compare it to what we found there, we know that it's identical. For part B, we're asked to use calculus to find the radius of the tank for which the surface area is a minimum. So we know that A is equal to this. What we really want to be doing now is we want to be differentiating this to find dA over dr. It's quite a simple one. We'll find that dA over dr is going to equal minus 12 over r squared plus 10 pi r over 3. Because we were interested in the minimum here, we want this set as equal to 0. So 10 pi r over 3 is going to equal 12 over r squared. Therefore, r cubed is going to equal 18 over 5 pi, once sort of multiplied on both sides and rearranged. And therefore, r is going to equal 1.046. And that's going to be to 3 decimal points. For part C, what we're asked to do is calculate the minimum surface area of the tank, giving our answer to the nearest integer. So for part C, quite simply, all we're going to be doing is just substituting it into this area formula that we found there. So 12 over 1.046 plus 5 pi 1.046 squared over 3, whack that into your calculator, and you'll get an area of something like 17 meters squared. Now that there is the answer to question number 13. We have finally made our way to the end of the paper. And for the last question, 14, in part A, what we're asked to do is to use the substitution u equals 4 minus root h to show that the integral of dh over 4 minus root h is equal to this here, where k is a constant. So really this is towards perhaps, say, the more difficult end of sort of integration, using more difficult substitutions, but really using a systematic method, it should be okay. So we're told that u is equal to 4 minus root h, and our immediate step should be to differentiate this, differentiate u with respect to h. So du over dh is therefore going to be equal to minus a half h to the minus a half. And we know then that minus 2 root h du is going to equal dh. This here is, and if we rearrange it in such a way where we take 4 to the other side and then times whatever we have there by 2, this here is 2u minus 4 du, and that equals dh. And if we were to multiply this out, 2u minus 8 du is equal to dh. And now our next step is just going to be to put it into here, once we've put this u as the substitution on the denominator. So we're told that 2u minus 8 over u, I'm going to integrate that with respect to du now, because we've swapped the du for the dh. And now what we're going to be doing is we're going to be cancelling that out with that, and then 8 is going to be divided by u. To work out that the answer is going to be 2u minus 8 ln u. Now we're just going to be putting in our sort of normal sort of h term into replace what we substituted it with. So 8 minus 8 ln 4 minus root h plus 2 times 4 minus root h. We multiply this out. 2 times 4 becomes 8, but that counts as the constant k in the question. So we'll have minus 8 ln 4 minus root h, 2 times by minus root h to make minus 2 root h. This 8 plus the c that we have on the end would become, just remember that plus c there, would become the constant. And that there satisfies that question. For part B, what we're asked to do is find, according to the model, the range in heights of the trees in this species. So we're told that a team of scientists is studying a species of slow-growing tree. The rate of change in the height of the tree in the species is modelled by the differential equation dh over dt is equal to t to the power of 0.25 times by 4 minus root h over 20. And in order to find the sort of the maximum value, should we say, of this tree, what we really need to know is, because the minimum value is obviously going to be 0, we're not going to get a negative value of the height of a tree, and obviously the lowest value is going to be 0, or the height can only be anything greater than 0. So if 0 is our lowest value, our highest value would be whatever we get when dh over dt is equal to 0. And if we set this equal to 0, if we multiply both sides by 20 and divide both sides by t to the power of 0.25, we get that 4 minus root h is equal to 0. 4 is then going to be equal to root h, and the h is therefore going to equal 16. And that there is going to be their maximum height. So h is going to be then given in the range of 0 and 16. For part C, the final part on the final question, we're asked, according to the model, given that one of these trees is 1 metre high when first planted, to calculate the time this tree would take to reach a height of 12 metres, giving our answer to 3 significant figures. So I'm just going to write that out, that differential equation that we had there. So we had dh over dt is equal to 2 to the power of 0.25 multiplied by 4 minus root h over 20. And just really put the h terms on one side and the t terms on the other. So we'll have dh over 4 minus root h will be equal to 2 to the power of 0.25 over 20 dt, because we've moved that dt to the other side. In reality, it's something different, but in practice, just think about moving that dt to the other side. And now we're just going to integrate both sides of the equation. This one here, quite handily, we had already done, and that's going to equal minus 8 ln 4 minus root h minus 2 root h plus k, and that's going to equal, and if we integrate this, we get that 2 to the power of 1.25 over 25 is the integral of that there. But we've got here a general equation. What we want to find out is the specific equation using this boundary condition that we have here. One of these trees is 1 meter high when it is first planted. So when t is 0, the height is 1. So we get that minus 8 ln 3 is going to equal minus 2 times by root 1, which is 1, plus k, and that's going to equal to 0. So k is therefore going to equal 8 ln 3 plus 2. So really what we can do then is just substitute that back into the formula. So we'll have minus 8 ln 4 minus root h minus 2 root h plus 2 plus 8 ln 3, where this here is our k value, and that's going to equal t to the power of 1.25 over 25. And our next step is finally going to be to substitute 12 into there. And if we substituted 12 into wherever we have h's, multiply both sides by 25, we'd get that t to the power of 1.25 is equal to 221.2795. And in order to find t on its own, we need to find the 1.25th root. I know that sounds slightly odd, but it does exist, of 221.2795. And that there is equal to what is approximately 75.2 years. And that there is the end of the paper. And that there was the Edexcel A Level Maths Paper 2 from the June 2019 series. If you followed on from the previous video covering Paper 1, it's clear that across both papers a lot of pure maths content was covered. So it's critical and imperative that you do well across all topics, across all chapters of Edexcel Pure Maths. It does form the bulk of your grade. It was certainly different in many respects to the previous paper, but at the same time I think that there were quite a few accessible questions in here, quite a few questions where it wasn't too hard to pick up marks and wasn't too easy to let marks go through silly mistakes. So well done for getting through this paper, and if you'd like more content like this, please like, comment and subscribe and just keep engaged, and yeah, we look forward to helping you on your mathematical journey. Please keep tuned for the next video.